you. Okay. This place working. Just check this is working. Okay, cool. So it is quite an advanced topic. So I actually break this down a bit, talk a bit more about concurrency in general first, so that we're all on the same page before I start talking about it in event sourcing. Little tiny bit about me. Been in the industry for about 20 years. Currently VP of Engineering at EventStore. Been programming distributed systems for most of those years and was doing event sourcing before we even called it event sourcing. So have some experience in that area. Concurrency has been the biggest problem I've seen bite systems hard when they go from development to production every single time. So I like to start with defining a few terms first, partially because these are all things that everyone knows, but they often have different meanings associated with them. I've tried to go with the definition because I find that makes it a bit easier, but it allows us to talk about what the problems are in a language that doesn't change, so we can frame it and understand those problems better. So the first one is, what do we mean by concurrent? And what that technically means is multiple computations being executed during overlapping time periods. So probably one of the earliest forms of that was multi-threading, where on a single CPU, whereby each process or each thread gets a slice of time on the processor to make some work happen, and then it gets changed for another one. That allows you to do concurrent programming on something which only has a single thread of execution physically. After that, we got to, there are other ways of doing it. It doesn't just, multi-threading is one way of doing that, so that's why we talk about multi-threaded, where you have more than one thread or execution context. You don't have to do concurrent programming using multiple threads. There are other ways of doing it. One of the common ways of doing it these days is to use things like promises, where you schedule a promise for a little bit of time, and you break up the work that way. It allows concurrent work to be done, because not all promises are necessarily working on the same piece of work. Parallel. Parallel is more interesting than the others because it actually requires dedicated hardware support. We were unable to do parallel programming without multi-core. As soon as multi-core came along, we were able to do parallel. That has often been referred to as the free lunch, but it makes concurrent problems much more easy to recognize and surface far more readily. The last one is asynchronous, because a lot of people use asynchronous to talk about those other three, but that's not what it means at all. It means to actions that execute in a non-blocking scheme. So when you execute your action, it doesn't block before returning to the caller, should it have anything that it needs to wait for. Obviously, most of this talk is about concurrent and what happens with concurrent access to databases in systems. So that's the one we're primarily focused on, but I want to make sure that we had defined what we meant by concurrent. Why do we care about it? The answer is generally, we don't. We generally don't care about concurrency most of the time when we're writing code. So that raises the obvious question, why do we care about it? Or when do we care? So we only care about concurrency when we have concurrent processes. We only care about concurrency when we're trying to access a limited resource. That's essentially a bottleneck, because it's limited to how many concurrent operations can operate at once, so we care about it for performance. We care about it when we're trying to update the same state, which is primary sort of like subject of what I'm talking about today. The reason for that is correctness. So let's have an example of why it might not be correct with no. So I've used this same example through each concurrency process model that I've talked through. Basically have two threads adding some numbers to an existing number, or two processes or two concurrent operations adding a number to an existing number. So if we think of those as execution processes, process 1 is going to read a number, or state A, which is going to have value of 100. Process 2 reads the same state. Process 1 performs the operation add 10 to A. Process 2 adds 20 to A. Process 2 writes 120. Process 1 writes 110. We've had two things happen at the same time. One adds 10, one adds 20. Answer should be 130, right? Yeah, this is immediately the thing that you tend to find, and you generally tend to find it when people are interacting with the database, because that's the most common shared state in most applications is a database. So, given that most of this is in database, what sort of concurrency controls do we have in databases? I'm assuming I should have asked this question. Has everyone written an application that talks to a database? Yeah? That's kind of why I chose database as being the example here. So it used to be easy when we just had a SQL database to talk about what concurrency meant. Now we have quite a lot of different options there, and some of them have some very specialized ways of dealing with it as well. So most relational database management systems, general SQL-like databases, allow you to deal with concurrency at a database, table, or row level. Not true of MySQL, I think that's quite hard to deal with it at database level. I think it's MySQL. They generally offer two options there, pessimistic concurrency and optimistic concurrency. And I'll go into more detail about these different models as well. The one thing that is fairly specialized, but is related to concurrency and event sourcing is column or escrow-based concurrency. Has anyone ever heard of escrow? I'm not sure I saw any hands then at all. It is really unusual. Most DBMSs don't support it. It's quite interesting. I'll spend a bit of time going over that because it is highly related to how we deal with concurrency and event source systems. So let's go through an example of pessimistic concurrency. So pessimistic concurrency, process 1 locks and reads state A. Process 2 is blocked from reading state A. Process 1 adds the 10. It writes 110 back to the database and releases the lock. Yeah, process 2 now acquires the lock. It reads 110, adds 20 to it, and the answer is 130. This solves our correctness problem. But our processes no longer make progress independently on the same data. Yeah? Optimistic concurrency. Both of them read the same state again. They don't take a lockout. They both add, as before, with no concurrency controls, 10 and 20 respectively, to the state. Then process 2 writes state A only, a state A to 120, only if it hasn't changed. Process 1 writes it to state A only if it hasn't changed. If process 2 did it first, it has changed, so you get a concurrency error, and you either have to retry or fail. And how you deal with that is often fairly interesting in most applications. Most people just retry. Is that actually correct? You know, I'll read the new state and then try and save my computed state again. That's invariably wrong. Often you have to do some recalculation of what the new state should be when you get that concurrency error. So that allows two processes to continue working, but actually one of them is going to have to reset and go back and do some more work. But it gets you closer to being able to do sort of like concurrent process, especially if one of those processes decides it's not going to update the state. At least it could read the state and make some progress there. Escrow is an interesting one. So nobody's ever heard of it, so nobody's going to know which databases support it. I believe that Oracle used to. The only other database that I know that supports it is JetBlue, which is the backing engine behind Exchange Server. Or it's often known as ECENT, which stands for Extensible Storage Engine NT, which gives you an idea as to which platform it's on. Why is it interesting? It stores a set of deltas to a column rather than an entire row. So it's the operation that was performed and the value. The operations must be commutative. That means that you must be able to apply them in any order and get the same result. Querying the column actually gives you back the result of applying all the operations. Yeah? So anytime you query the column, you get back a rolled up state. You don't get back all the operations, just the current state that's calculated off those operations. Those of you familiar with event sourcing can see why this is relevant. There's no access to the underlying operations after making them. So while you get the rolled up state, you can't see what those operations were to get to that state. And the storage engine may periodically underneath snapshot the rolled up state to reduce the number of operations that need to be applied to calculate the state. Again, people who are familiar with event sourcing will know that snapshotting is a standard way that we try to deal with having lots of events that we need to try and deal with. What happens with escrow then? Process 1 writes +10. Doesn't need to read the state because it doesn't need to calculate anything. Any subsequent operation will get the rolled up version of that at being 110. Process 2 writes 20. Same problem, same thing. Yeah? This is much easier to perform concurrent updates on a column without having any issues with concurrency at all. Because you're not directly modifying the value, you're actually allowing that to take place later. And by that I mean you're not directly modifying the value of the current state. Right, went over this a bit earlier, but I'll review. There are problems with each of these approaches, even with escrow. So pessimistic gives us the problem that processes are now sequential, not concurrent. It can be tuned by lock level. So if you've got multiple rows in a table, then you don't necessarily have to be pessimistic across the whole table. You can be pessimistic for each row in the table, which gives you some ability for processes that are updating different state or different rows in that state to work concurrently. And when you're dealing with multiple resources in databases, if you're not very careful about the order in which you acquire locks, you get deadlock. So now your application doesn't get anywhere. Most databases deal with that by timing out when you deadlock or killing one of the operations which was deadlocking. Puts you back in the same problem of optimistic concurrency where one of you has to try and do some more work again. Optimistic. All processes that you write must deal with retries. Yeah? It's easy to deal with one data point when you're dealing with retries, right? Yeah? What happens if you are in a SQL database and you've updated 2 tables? Yeah? Which one had the concurrency error? Yeah? What do you do about that concurrency error? What happens if your operation actually should succeed in one of those tables and not in the other? Suddenly there's a whole bunch of questions that happen here because you are not talking about necessarily just one state because of the way the storage engine works. You can actually broaden this to deal with multiple states. And actually, the way most people deal with retries is they just try again after getting the new row version and overwrite the old data, which gives you the same problem that you had with no concurrency controls in the first place. It uses finer grained pessimistic locks than the than the pessimistic locking, where when you read the data, you take the lock, but it's still a pessimistic lock at the point of update inside the database engine. Yeah. Again, when dealing with multiple resources, it can result in deadlocks. One of the classic performance problems that I dealt with more than once over the course of my career is our database is going slowly. Why is that? Lots of deadlocks occurring, lots of processes retrying against the same set of tables, deadlocking again. It tends to lead to, when it's working well, it can work quite fast. Once it starts going badly, the performance can tank really badly. And that's usually the time that most people realize that they have a problem with their concurrency control in their database. Why is it usually the first time? Because it's very hard for most people to figure out that they actually lost some data with a last one writes scenario. Because unless you have some way of tracking it, one of the things about updating state in place is that you don't know what the previous state was. You only know what the current state is. So you end up having to try and figure it out through logs, tracing, some application level thing that you do. There's not much help for it. The database engines are just like, yep, you want to update that? Fine. New state. Problem solved. They lie a bit because internally they know exactly what happened in the transaction log, but that is something which is not exposed to you. escrow. So escrow sounded like it was going to fix the world, right? Unfortunately, it only works with numeric columns. Who only has numeric data in their database? Yeah, not many hands at all, like none. It's limited to commutative operations. Who only does commutative operations on their data? No. I think Oracle dropped support for it. Pretty sure they dropped support for it, which means you've only got one database on one platform which supports it. So why am I even talking about it? Right? Because it's quite interesting and very applicable to event sourcing. Most systems want to update more than one column in the same instant. So they end up falling back to pessimistic or optimistic concurrency, even in the one database that supports it. So it's almost good, right? So, I know this is an event sourcing track, but people have different definitions of event sourcing. So again, I want to make sure we're just all on the same page before I start talking about event sourcing, concurrency and event sourcing, and different techniques we can use inside it. So it's a persistence pattern that can be applied at the service level. Yeah? That makes it a tactical pattern, such as using model view controller or command query responsibility segregation. Yeah, it is not a top-level architecture. I do have, for those people who want to know the difference between event sourcing and top-level event-driven or event streaming architectures, I have 4 slides at the end, because it's the most commonly asked question I get after I've done this talk, that have nothing to do with concurrency at all, but just to head off those questions. And they're kind of useful. So, and this slot is a bit longer than I normally give the talk in, so I've added them in rather than having them in for the questions at the end. So what is it that makes it different to normal database operations? Persisting changes to application state as an ordered sequence of events. Yeah? You can then calculate application state by replaying the history of those events instead of directly reading from it. That is the difference between most RDBMS, document stores, and escrow, which is why I was talking about escrow. Yeah? We store the changes to state. The level of granularity for concurrency is the event sequence. Yeah? There are times when you don't particularly care what order the events are in, as long as they're in there. Yeah? Not always. Most systems that's not true for. But in that case, you can relax even that concurrency guarantee, which gives you the ability to have more processes accessing that concurrent state, as in the event stream itself. Writing to multiple sequences, or what you might call a stream of events, writing to multiple streams of events, is generally prohibited by most storage engines out there. So databases that are specifically designed to deal with event sourcing, or database schemas that are particularly designed to deal with event sourcing, most of the ones that I'm aware of, they don't allow you to write to multiple streams at the same time. Why is that? Because that puts us back in the same problem we had before, where we ended up with potential for deadlocks in the system. And the other thing is, it explodes the amount of space you have to reason about for your concurrency issues. Because, which one? Should I apply to this one, not this one? Should I make, what should I do when I'm dealing with multiple state? Trying to figure out how to deal with problems updating that state becomes very quickly very hard. What concurrency models can it support? Well, most data stores that allow you to store events or use event sourcing will actually allow you to do optimistic or escrow. So escrow is literally where you say, I don't care about the order because I know it's commutative. Optimistic is where you say, I want to append this sequence of events should there have been no changes since I read my state. That can be done very simply by just checking the event sequence number of the that you're trying to write to. Some implementations can support pessimistic, but most do not. So any event store that's written on top of a SQL Server instance could support pessimistic locking. You probably wouldn't want it to, because your events are probably distributed throughout a table, and by the time you decide that you're going to take a pessimistic lock on all of those rows, the database engine will go, yeah, that looks like a table lock to me, and then you've just put a lock across your entire data store for your update. So most of the time, you wouldn't even think about doing that. So what does optimistic concurrency look like with event sourcing? So I talked a bit about stream positions there. Process 1 reads state A of 100 at sequence position 4. What does that mean? That means that process 1 reads all of the events up to sequence position 4, calculates that the current state is 100. Yeah? So it's doing a bit more work in the process to calculate the current state rather than just going, give me this row. That's my current state. Right? Process 2 does the same thing. Process 1 generates an event, say added 10. Process 2 generates an event, say added 20. Process 2 adds 10, appends that event, only if the sequence position of that stream is still 4. Yeah? Position is now 5 after it's done that, and subsequent reads will calculate state to 110. Process 1 appends added 20 only if the sequence position is still 4. Process 1 gets an error and retries or fails. Pretty much the same as you get in database, right? Not much has changed here. Yeah? That is quite often the case for most event-sourced applications when they're dealing with updates to state. You will almost always be using optimistic concurrency. Yeah? But there are some tricks you can use to get around the problem of not being able to figure out whether or not you just retry. I'll cover those in a bit. escrow, EventSourced. both read by calculating state at position 4. Both generate the same events that we just talked about. They both append. The position moves on, but they don't care. Yeah? At any point in time that anyone comes in and reads, either if the position is at 5 or if the position is at 6 after both processes are appended, they will get the correct state. Differences between ESCO and event sourcing. Events can contain any payload you want. You are no longer limited to numerical values. It is, however, still limited to commutative operations. However, that generally tends to mean commutative at a business level. Yeah? I changed my address and someone else changed my credit limit are two completely different operations that have no conflict. And the state, the roll-up of my state, ends up being correct regardless of the fact that we didn't use optimistic concurrency. So sometimes when you're building your system, you can identify that all of your events that you're writing for a particular stream, they're all commutative, at which point you don't need to care about order. If you're using event store, you can just stick expected version any on, and it will just write the events, and you don't need to care. It's kind of cool, because you now don't need to buy, if you're trying to do that in RDBMS, it's actually really difficult, because you really do care, because when you update, if you're updating something that someone else has updated, you cannot tell if you've got a conflict. You actually have to go and read the change. In order to be able to figure out whether or not you can actually apply the changes that you wanted, you need to go and take the original version that you read, your updates that you tried to make, and the updates that were made by making a delta between the original version that you read and what's currently in the database, and then you can figure out whether or not it's okay to just apply your update anyway, despite the fact that the row version of the database has changed. That's quite a lot of work. It's non-trivial. You have to do it for every single thing that you're looking at. Differences with the optimistic differences with event sourcing. You always get a complete view of what changed, right? So when you do get a concurrency failure, if you want to know what's changed versus an RDBMS, you don't have to do all of this calculation. You can just say, well, I started there. In order to know what's changed, I just read forward to the end of the stream. That gives me a list of everything that changed. Yeah? That will allow us to do some more interesting things later. There are some requirements for data stores that support event sourcing. You must be able to conditionally append to the stream based on sequence position. If you can't do that, you're not doing event sourcing, because you're not drawing changes to application state, you're publishing a sequence of events. That's very different. You must be able to append one or more events into a stream in an ACID transaction. The reason for that is event sourcing is storing application state as a sequence of changes. Changes to application state logically does not mean that you can only do that one event at a time. You may produce a set of events that you want to store together. That can help you when you're trying to deal with conflicts, because maybe some of those events don't need to be solved, or you're only some of those events when in conflict. That gives you a much smaller area to look at when you're trying to resolve your conflicts. So we talked a lot about how you get conflicts, and I'm pretty sure that from the title people are more interested in how you deal with them. There are a number of options. None of them are necessarily wonderfully easy. There's no silver bullet here, right? But they are fairly similar to operations that pretty much most developers deal with on a day-to-day basis, because most of them can be likened to Git or Git operations. Who here uses Git? That makes this bit a lot easier. So that was pretty much everyone. So the first thing you can do is if all operations that have occurred since you last read your state are escrow, and you determine that by understanding your application. There is no event store product out there that will ever be able to understand your application without you telling it something. So you have to do that work. You can just go ahead and try and save the events again, because nothing is going to change the state to something it shouldn't be. You're not going to lose the history of what happened as you would in something like a document store in RDBMS. You have the full history. You know that those operations don't conflict. So, and they can't conflict because they're escrow style events, they're commutative. It doesn't matter what order you apply them in. So you can just do it. Yeah. This is pretty much like a Git pull where each of you have only changed separate lines. Yeah. So if you think about that, all that happens when that happens is you get all of the line changes all together. Yeah. You can't tell by looking at the end state which order they happened in, but it doesn't matter because the order doesn't matter. Yeah, it's the same with your application state. It doesn't matter which order they happened in. You get to the same end state. If all events are the same as what you just attempted, or even if not all of the events are the same as what you just attempted, if your events that you're trying to write are included in the set of events that have changed since you last read state, just return success. Don't try again. That's where two of you have made two commits and just have exactly the same changes. Yeah? Very easy to merge. Yeah, no one cares. It's the right state. Carry on. That is way easier to do in event sourcing because you know the type of events that you've got, so you know what the changes were. You know the data that's in them. Usually your events are small enough that actually figuring out if the data that's in them is the same is pretty easy. Yeah? I would strongly advise against huge events because this makes a lot more problems for yourself. And takes away a lot of the benefits of event sourcing. Because you have the exact changes that were made, both by you and whatever processes wrote data to the database before, it is possible to write a conflict resolution process against those things. Yeah? How difficult that is depends on your application. So, updated address and changed telephone number might both technically update your address state. Yeah, but you can tell they don't conflict. Whereas two attempts to change the address, one to the other, they do conflict. Often the answer is not automate the conflict resolution process, but give it to a human. Which one of these should succeed? Yeah, but that is a valid conflict resolution process that you can go through as part of sort of like an alerting escalation pattern into the business that probably has business value. Maybe not changing address, but there are quite a lot of other things which would have business value in that case. Yeah, this is a bit like a pool where you need to do a merge and you need to have someone involved or some process involved in making decisions about how you should do that. If you think about it, where you write your conflict resolution process, it's a bit like having a well-known set of changes. So if you use get so you've already made decisions about how to solve those conflicts, record those in your application, automate that process. The ones you can't do, here, you deal with it, human. It's a valid strategy. Almost impossible to do if you're not storing the changes. because it's really hard to make a decision based on final state which one should win. The other thing you can do is you can reset your application state. If this is something that you have to deal with a lot, you can put infrastructure in your code to deal with this. So once you've rebuilt the state from the application, you can snapshot it before attempting to perform the operation and getting the events out the other side of it. Easier in functional programming because you don't end up changing the original state. Now all you need to do is get the new events, apply them to the old state, and then try your operation again. Yeah? If it succeeds, great. You can carry on. You've got a new state which is valid according to your business rules. Yeah? If it doesn't, then maybe the operation that you're attempting is no longer valid to be doing. In some systems, especially ones which emit more than one event based on decisions they're making based on state, if the state has changed, the operation that you try after you've rebuilt that state may produce a different sequence of events. That's still valid. Yeah? It is often very difficult in other systems to be able to do that different sequence of events based on the state which has changed. It's not impossible, often not easy. So I've talked now about how we deal with conflicts and how that differs to relational database systems. I've talked about how we get into those conflict situations, the different levels of concurrency control that we have, both in traditional databases and event sourcing. Before I move on to the next bit, which is heading off the other questions that generally tend to come up, does anyone have any questions on the concurrency aspect of this talk? How to identify the conflicts? Yes. So the question is, how do you identify the conflicts? So most event sourcing systems, you tell it what's the sequence number in the stream that you read your state from. Yeah. So the way that it identifies the way the database identifies the conflicts is that sequence number is no longer the same. Does that answer your question, or was there? Okay. So you shouldn't be storing the event sequence number inside the event, would be my answer to that. So the question is, do you bump the sequence number of the stream if you want to save that event? That to me says that you're storing the sequence number inside the event, and sequence number is essentially the equivalent of row version, and you should not touch it other than to know what it was. So yeah, so often you see people, they will store like the aggregate name and the event ID and the event number inside the event. Often the event ID as well. That is not a good plan, because you should allow the infrastructure which deals with your concurrency to take care of knowing what those things should be and just accept what they are. Because if you don't do that, it makes it really difficult to figure out whether or not you're getting concurrency issues. If you store event ID in there, it makes it very difficult to figure out whether or not you are doing idempotent writes. Yeah. One of the things that you can do if you don't store event ID inside the event is you can compute the event ID based on the event type and the data inside the event, which allows any event which is exactly the same to be an idempotent write for stores that support that. Yeah. Any more questions? Yes.
Yeah. Just wondering about, obviously, touching other systems. Usually you have application logic that causes some side effect in the third-party system. Payment provider, notifications, something like that. then records an event. Let's say that you have a business logic problem, therefore this event cannot be put in an escrow system. So you have some locking and you cannot really retry this operation. Is there a common pattern, or is it just something that failed and that's it?
So the general way that you would approach that particular issue is you wouldn't attempt to write an event to say, I want to make this charge, call the charging system, and then write an event to say, I've paid this charge. So you're not interacting, so you try and avoid that interaction. The way you do it is you would say, you go into your stream and say, I want to make a payment charge. You would then use something which is part more of an event-driven architecture, which is going to react to that event being written. It's going to call the payment processing system and make the charge. And should that charge work, it's going to write back that the charge was made. The fact that that charge was made, cannot be argued with. So that is not an operation that can fail. So you do not care if your state has changed if you've made that charge. What you might have, if you've got order cancellation going on at the same time, is you might have to have something sat there to detect problems where you've charged someone's card whilst they've been cancelling the order. And that is definitely on my next slide. Now I understand why the microphone's in a big red box.
So is it fair to say, using the examples you gave, that each aggregate has its own stream?
Yes.
And would that be typical?
Yes. It is also possible for an aggregate to have more than one stream, but that is a fairly advanced use case. And if you're interested in that, you can talk to me about it afterwards at lunch. One more down here.
Don't record me throwing this.
Hello, but just comparing the sequence number doesn't give answer if there is a conflict. If one event change email, another change first name, then it's no conflict. We can apply
okay. So it doesn't tell you that there's a conflict between events. It tells you that there's a conflict between what you thought the state was and your attempt to update it. The way you find out the conflicts is you then read forward from where you thought the state was. That will give you all the events. It is your job as an application developer to figure out which of your events conflict and which of them don't. Now, that is code that you will have to write. But that is code that you end up having to write in any system. But because you know what the events are, that gives us the ability to say, okay, for this known set of events, we know that these don't conflict. We can make a decision based on what these operations are and what data is contained within these events, that these events don't ever conflict. And you can have your system automatically deal with that problem. So that gives you a second set of events that your system can't tell if they conflict. Those are the ones that you want to escalate up to someone and say, I don't know what to do here. But that tends to be a smaller set, and it tends to be easier to deal with. But you do have to design your events with the idea in mind that you do not want to say, aggregate updated all of the fields.
So basically this is sort of optimistic log, but then application just decide if those events need to be, I don't care about those new events, just save my new event.
Yep, so the thing that event sourcing gives you, and the thing which makes it different to most other concurrency and most other databases, is that you can make intelligent application level decisions. You still have to make them, but you can actually put them in and do exactly what you just said. Say, yep, don't care about these were fine. Just try again. The reason you can't just say, just write them straight in, is when you try again, you might have another conflict with some that do actually conflict that you can't resolve in that way. So it tends to be just try again. Usually in most systems, unless you have designed your system in such a way that you end up with a lot of competing writes on the same stream, usually in most systems, you will go around that loop once. Yeah? But for very hot streams, you probably need to be doing this in memory and a lot faster. And also do something to make sure that those changes are not happening on independent systems. The thing which springs to mind is trading. Yeah? If I'm dealing with trades against an order book, I generally want to keep that order book in memory and make sure that all of the trades against that order book go to the instance which is in memory. That does two things. One, I'm not going to get any conflicts because it's only going to a single order book instance in memory. And two, it's a lot faster because I don't have to hydrate state every time. Yeah? But that is one of the few systems that I can think of where you genuinely have a lot of updates going into a single stream. Most systems, if you're doing that, you've ended up with the wrong design. Any other questions? Okay, I'll take this last one, then I'll go on to the additional slides. Who has my microphone?
Hey, sorry, I'm just wondering, you probably already even answered it or at least mentioned it. I'm just wondering why you haven't mentioned actor model, for example. Actor model like Akka or Long, whatever.
I just did with the order book.
Yeah. Yeah, but it was not like you just mentioned, but
right. But that evolves the problem. That avoids the concurrency problem in a completely different way, which is why an order book would do it in a completely different way, where you're sending things to an inbox of something which is remaining there to process it. This was more how do you, and if you don't have concurrency problems, as in you've avoided them by using a different model, this talk gets very short. It's like, use the actor model, bye. Okay, so I often end up at the end of this talk with people going, but hey, what about this? And they start talking about something which is event streaming. Or, hey, what about this? And they start talking about something which is event-driven architecture. The reason event streaming comes up is there's a lot of examples out there for doing event sourcing that are actually event streaming. And the reason that there is a difference is because there are no concurrency guarantees on event streaming. You're just writing a sequence of events into something. You can't tell if the sequence number has changed from when you last read state. So you cannot detect conflicts at all. You can detect them later when you're reading through it, but you can't detect the conflicts when you're making the updates. And that's quite an important difference because we're storing application state, and if I can't tell that my application state is no longer valid when I've written the events, I end up with invalid application state that I have to deal with somehow later. Yeah? Most event streaming systems don't partition at the aggregate level. Yeah? So now I don't have to just read events for the state that I'm interested in, I have to read events for states that I'm not interested in too. It is really useful for things like Internet of Things style applications where you've got a lot of data coming in from multiple sensors. They don't conflict. They are just events. Yeah? There's no application state being updated. It is just a fact that happened. One of the things it does, which is quite important, is it does decouple the producers from the consumers. That's often what people are really trying to do when they start going down sort of like the event streaming route. Does it have application to event sourcing? It can do. Yeah? It can be used with event sourcing to distribute those events for further processing. That's a very valid reason to use those kind of technologies where it's just events, here they are. because we've done the bit up front where we care about application state and the concurrency model of the application state, we don't care about it afterwards. Those events have happened. There's no concurrency operations that can happen on them. They can just go through a streaming system and be consumed. The last part is really important. Yeah? If you're going to be using event sourcing, yeah, it's a private persistence strategy within your service. Don't publish your private schema. Yeah? If you're going to do event sourcing and event streaming together, you should have a public schema that you take your private events and you turn it into that public schema before publishing them on the streams. Because otherwise, when you change your downstream, when you change your data inside your service, someone over there breaks because they thought that they were going to get this exact schema forever. Yeah? You need to think about versioning. It's like calling any service, it's just that you don't know which service you're calling. You know, all of the standard tenets of dealing with breaking contracts in all service-oriented architectures that we've ever dealt with apply here. So remember that they're public as soon as you push them out into another system that is not your persistence for your service. Event-driven architecture. Who knows what event-driven architecture is? That's no one. So a lot of event streaming architectures are talked about as being event-driven, but they are subtly different. Event-driven architecture is basically a SOA architecture with an event bus in it. So you don't make calls to other services and say, hey, do this. You publish an event saying, hey, this thing happened. And another service on the event bus is subscribed to that kind of thing. And it's going to take an action off the back of it. Again, it decouples the producers from the consumers. Not necessarily exactly the same as event streaming, because event streaming generally tends to say, yeah, I'm going to partition things like this. You're dealing with usually ingress. It's usually for ingress systems. And it doesn't involve a pub-sub mechanism. Yeah. You can build these things on top of each other. There are features of these things which can work, but they are different architectures. And they exist for different reasons. Subscribers will often watch for interesting sequence of events and publish further events. Yeah? And a good example of that is fraud. Yeah? Fraud detection systems will look for interesting sequences of events across accounts. Yeah? And say, oh, that looks like it could be fraud. So, possible fraud discovered. Yeah? That may then be consumed by other things that are looking for patterns of possible fraud discoveries to actually improve the algorithm. And do all sorts of things with event-driven architectures. They tend to be very, very loosely coupled. Again, with event sourcing, you can use it to distribute the events for further processing. And again, if you're going to put event sourcing anywhere in event-driven architecture, what you're using for your event sourcing, yeah, those are your private events. It's your private schema. Don't publish your private schema. The other thing about those two things, about both the event streaming and the event-driven architectures, is that you often want to aggregate up some of your events, so you're not publishing necessarily the same fine-grained manner that you might use internally. Because it makes it very difficult for people downstream to consume what is a logical operation outside of your application, which inside of your application may be more than one logical operation. Okay. How does CQRS relate to event sourcing? Applications tend to query more than they write. Yeah. We use event sourcing to give us less conflicts. Yeah, but that's the write side, so we don't want to forget about the reading side. Yeah. So CQRS deals with the fact that we're playing events to get the answer to give me all the customers whose name starts with whose first name is James is probably a really bad idea. Yeah, read every event you've ever written to see if it says customer's name was James or has been changed to James. Yeah, that's a lot of events to read to answer a fairly simple query. So what we do is we produce different models to optimize those reads. Yeah, usually into a relational database management system because it only cares about the current state. Queries tend to only care about the current state. Not always. And if you've got queries that need to deal with event source, with sequences of events, you generally tend to want to run those in something which is either queryable or have something like an event processor which actually just looks for those and then writes out something when it finds something interesting rather than doing ad hoc queries on it. The storage service that is part of the same service boundary along with the query model. So wherever you're storing those queries, the service boundary, yeah, which is these operations, yeah, inside of that is your query store and your write store. And those are private to that service. However you choose to make them private is entirely up to you, I don't care. Right? But those things should not be shared directly with other services. That's all I've got. I've got about 2 minutes left for questions, so I'll probably not take any now. So if you've got any more, please feel free to come and find me. We have a stand about there in the hall. I will be hanging around there for the next couple of days. Feel free to come and ask me or anyone else for questions. Also, I am generally available to contact. I get a lot of emails because I do this. That means that if I don't answer you within a couple of days, your email probably disappeared off the unread list faster than I had a chance to even see it arrived. So feel free to bug me more than once if you need to. Should have put the DDD Secure ICS Slack list up here as well. For those of you that are not aware, there is a Slack list called DDD-CQRS-ES. It is free to join. I hang around on there, and if you @me with the same handle as the Twitter handle, I will respond on there probably more frequently than via email or Twitter, to be honest. I have also on GitHub have a few examples of various different things you can do which are interesting with event sourcing and aggregates. Okay, thank you.